Hello, today we're going to talk about displacement current and how it involves Ampere's law and Gauss's law. And as a quick reminder, for Ampere's law, if you have a current carrying wire, and we're going to assume positive current here, then a magnetic field goes around that wire. And the magnetic field there'd be circles, and the field would go that way. Okay. And Ampere's law, which we're going to need a lot right now, is closed loop path integral of B dot ds equals mu naught times I in. And for the most part, for a straight wire, your path, your ds is, you're looking to integrate one of these circles, and so basically you're just taking b times ds all the way around. That ends up being b times 2 pi r equals mu naught I in. All right, so that's all well and good, and that's review. Well, what's displacement current? Okay, well, let me explain. Let's say I have a capacitor, and I'll kind of draw it a little funky here. Let's say there's a wire feeding the capacitor. Here it is. Here's one plate of the capacitor. And then here is the parallel plate of the capacitor. And then here's the wire coming off the other plate. Okay. And let's assume that there's positive current flowing this way to charge the capacitor up. So the left-hand plate's becoming positive and the right-hand plate's becoming negative as time goes on. Okay. Well, looking at Ampere's law, back in Ampere's law, we have mu naught I in. And I in is how much of this current passes through or pokes through the area bounded by your path that you chose. Okay, so like from the case of the wire up there, all the current goes through that area, and so your I in would just be I. Okay, now as far as that current poking through that area goes, by definition, it's the current poking through any area you want that's bounded by this path. Okay, so most of us, when we think of that, we think of this path as just being like, hey, it's the area of the circle, and the rim of the circle is our path, our path that we're going to integrate for b dot ds. Okay, but here's what I want you to imagine. Imagine you take that circle, and imagine it's instead of like a hard surface or something, it's flexible, like the neck of a balloon. And let's say you start to blow the balloon up. So this green area starts to kind of expand like that. Okay, it's kind of an ugly balloon, but that's what we're talking about. Imagine you took this area, instead of making it this, you blew it up so the area now went like this. Okay, that area is still bounded by our path. That's this guy here. Okay, now I'm going to recreate that down here with the capacitor. So if I asked you to find, let's say, the magnetic field here, okay, you would draw a ring around that wire, okay, and you would, for your integral b dot ds, it would be a circle, b times 2 pi r. Your I in would be all the current. Okay, so that's if your area is this thing here. Well, what if I take that area and blow it up such that, imagine this as being the very bottom of a balloon, and you blow it up so it kind of looks like that. Okay. Well, if you look at that real careful, that area is still bounded by this ring. Okay. But no current passes through that area at all. Okay. There's no actual current. There's no electrons, or if you think of it as positive charge, there's no charges passing through that area. So what do? Okay. Does that mean there's no magnetic field over here this wire is? Well, of course there's a magnetic field there. There's a current passing through there. So we have to modify Ampere's law significantly to account for this lack of an I in that particular area. Okay, so it turns out that Ampere's law is actually called Ampere and Maxwell's law when you put these two together. But Ampere's law becomes the following: closed loop integral b dot ds, that doesn't change, okay, but that equals mu naught times two things, I in, which we're used to, plus I d. And D is what we call displacement current. It's kind of like an imaginary current that passes through this, this surface that we've kind of blown up, okay? Now, having said that, there's some other background we need to talk about before we can start doing calculations with that. If you'll recall, we have Gauss's law. So let me write that out over here. Okay. Gauss's law, double integral E dot dA equals Qn over epsilon naught. Okay. And we know net electric flux is equal to Qn over epsilon naught. So this is three things that are kind of equal. Net electric flux leaving an enclosed volume is equal to Qn over epsilon naught, which is then equal to double integral closed surface E dot dA. We usually use Gauss's law to find the electric field somewhere. But we're going to do something a little different with it now, okay? So what I'm going to do is I'm going to take this last thing and solve for Q. So Q equals epsilon naught times electric flux. So I'm going to lose the net, but it's technically there, okay? And then I'm going to take the time derivative, okay? dq dt would equal epsilon naught, well, that's a constant, and then times the derivative of the electric flux with respect to time, okay? We call that displacement current. This is like the imaginary current that is passing through that surface that we drew up above with the green with the x's, okay? Now, that's also the rate at which the capacitor is actually charging, okay? So displacement current is the rate at which the capacitor is charging, which if you go back up to the picture here, let's say this current right now is 5 amps. Well, displacement current would also be 5 amps total, because that's the rate at which the capacitor plate's charging, okay? Now, this is significant, and by the end of the semester, I'll swing back around and talk about this. So what you're getting here is you're getting a change in electric flux. And for a capacitor, electric flux is E times A, and A don't change for a capacitor, so what you're looking at is a change in electric field. This term is going to go in up here. That's your displacement current. So if you have a change in electric field, you then get a magnetic field. So in class, we've talked about what causes magnetic fields, moving charges or current. Well, that's not always the case. In this case, a changing, and that's a key word, this changing electric field creates a magnetic field in between the capacitor plates, okay? Now we can kind of put this together a little bit. For a capacitor, we say the displacement current is equal to epsilon naught, and then the time derivative of the electric flux, which is E times A. But for a capacitor, area is fixed. It's a plate, okay? It doesn't change. So we kind of rewrite this as displacement current equals epsilon naught A d electric field dt, okay? And so we're going to be, and that's equal to dq dt. That's the rate that you're charging the capacitor plates, okay? So in the next video, I'm going to show you guys we're going to actually do a calculation with this. Now I'll make one more note before I switch off and do a different example of the calculation. Looking back at this picture here, what that means is there's going to be a magnetic field in between the plates. In the example, I'll show you what that magnetic field looks like, and I'll draw a much neater picture. But one thing I want you to notice, if I draw an Amperian loop here, like so, okay, will all of the electric field that goes between these plates, will all of that field go through that loop? Well, no. So in our example, we're going to have to account for figuring out how much of that electric field changing goes through that loop. So the next video, again, will be an actual mathematical example, which will be like chapter 34, the RP that we've assigned to you.